Alright, so my name is Jesse, and I did my oral presentation on experiment number 5, which was the initial rate method experiment. So how this worked was you would do a couple simple reactions, and you would record them, and you'd use the results of that to find a bigger reaction, the rate. So basically, the simple reaction was you would take a mixture of oxalic acid and water, DI water, and then you would drop potassium permanganate into it and then record how long it took. And we did this at varying concentrations and volumes. So some of the materials we're going to need are, first you need the Spec 20, which is used to calculate the transmission percentage. Then we have oxalic acid, which is, I did some digging on this stuff because I was a little bit interested, or one of the two, I don't know. But oxalic acid is actually wood bleach, so if you ever have anything on your hardwood floors that you want off, it's a place to go. Potassium permanganate, I also looked up, and it's iron out, and tons of YouTube videos of people catching stuff on fire with it, so fun stuff. You needed a stopwatch, some test tubes, cuvettes for the Spec 20, you had to transfer it, and then the DI water. So the experimental procedure is pretty much what I said earlier, but to go a little bit more in detail, what you're going to do, you start out with the DI water, and then you measure out the OA, or oxalic acid solution, and you mix those together. And then you would go to Dr. Jean, and she would drop your potassium permanganate. And once you spun that till it turned purple, well, first you start the stopwatch, then it turns purple, and then you put it in the Spec 20. And once it reaches 30%, you stop the timer and you record it. And you're going to do this a couple times for each different set of concentrations and volumes. That's actually up here. You did it twice for each of these, each different experiment number, and you would average the times. So here are the average times actually. So in order to find the rate of the reaction, which was used later on, you would first have to convert the molarity of the stock solution of oxalic acid and potassium permanganate, actually the potassium permanganate, just the KMnO4. And it was at 0.013, I want to say, and once you converted it, it came out to 0.0108, and you would divide that by its coinciding time, and the rate for that came out to be 3.28. This is just a sample. The actual equation is over here. Once you have that sample, or once you did this for each experiment, you would end up getting different results. And I kind of have to skip forward to make sense of this. Your different results ended up coming out in a bit of a ratio thing, and this is somewhat different. I know Dr. Jean, I showed her this with it's how I learned it in high school. It's different from Devon's. You didn't solve for XMR. You look strictly for ratios, and you would take the ratios, and if you look how 2 is held constant here, the KMnO4 is held constant, it's both at 2. This doubles. This is, it's not quite doubling, it ends up, it's a factor of 1.56, I want to say, ended up giving you 0.7 as an exponent. And as the ones were held constant, this doubled as well as this doubling, so it is still a 1. And because of that, you would get an order of 0.7 for the oxalic acid, and for the KMnO4 you got 1. So you would plug that in. You plug that in to find the rate constant into the equation, and that is rate equals K times KMnO4 to its power, or its order, times oxalic acid to its order. And once you did that, you would get a rate constant of 6.8 times 10 to the negative third. And that's, the units are meters, 1 over meters times seconds. So the discussion pretty much just asked how you would go about finding the rate law using this method. This is actually different. I did this 2 separate times. This is before I saw Dr. Jean because I've changed my method to it. I used M1B1 equals M2B2, but this is separate. Anyway, you find the molarity of that, and then once you divide it through and get the rate, and you compare the rates, that's how you would find the rate and the rate constant. So, the next slide is just my references, and they're the same as everyone else's, so thanks.